When I was about 13, I visited my dad's native country of Haiti. My parents took my siblings and I there to visit, and this was a really eye-opening experience for me. This was the first time in my life that I had really seen what poverty was. And at that age, I realized that in countries like Haiti, there's a lot of things that they don't have that we have in the United States that we really take for granted. And those are things, infrastructure like buildings and bridges, safe roads, paved roads, clean water, street lights, all of those things that really make civilization and society run. And so at this young age, I wish there was something that I could do to help bring this infrastructure to the country, but I didn't know what that was. And it wasn't until a few years later in high school when I learned about what civil engineering was, and I learned that civil engineers are the people who make this possible, who bring infrastructure to society. So now I'm a graduate student in civil engineering, and I do research in how civil engineering structures break. So civil engineers and researchers like me are interested in things like how much, take a building, say, and it's under an earthquake load, or a bridge under really high winds. So we want to know how strong does that wind need to be, or how severely does that earthquake need to be shaking until the structure would fail. And of course we don't want that to fail, so we want to design so that that doesn't happen. And of course it's not like we can go out and build a bridge and then make an earthquake happen and see how it's going to fail. So instead what we do is we step back and we develop models. We write computer models so that we can represent this phenomena, an earthquake or wind, on a bridge or a building in the computer, and we can get information about what's going to happen before we even start any construction at all. So civil engineers use computer science to make these models, and one way that civil engineers might make this model is, instead of solving the problem, let's take the problem of a balcony, for example. So let's say that we have a balcony and the engineer wants to design it, and they want to put a really heavy air conditioning unit on the end of it. So we want to know, can we do that, or is it going to break? And so one way we could do this is we make a model of a balcony, but we can't just tell the computer model a balcony. Instead, what we have to do is we actually break that balcony up into a bunch of little sub-pieces, a bunch of little sub-problems, and then we can feed that to the computer, because the computer can handle a bunch of little things. So the computer does a bunch of little number crunching and then brings it back, puts it all back together in the way that it was, so that we know how our balcony responded. But we might have to break our balcony into like millions of pieces. And so it's really important that those pieces are sorted so that we know what order we're doing all these calculations. And then so when we put them back, it's in a proper order, so we actually get a balcony back and we know how it responded, as opposed to just a jumbled up mess. So computer scientists are very interested in sorting algorithms that can do things quickly and efficiently, so we can solve problems that actually impact society.